Hello, everyone. My name is Nia, and welcome to today's webinar. We'd like to give everyone a minute to join and settle in. Please use the chat to let us know where you're tuning in from. I myself am tuning in from New York City, and we have Apoorva Joshi on the call, who is tuning in from California, and she is our senior AI developer advocate today, who is going to give you a wonderful presentation. But make sure you are putting where you're tuning in from in the chat. There may be someone attending this webinar in the same location as you.
Hi, everyone. Thanks for tuning in.
Hello, good morning, good evening, good afternoon, because I know we have people from all over. And make sure you're responding to everyone in the chat because there may be someone in the same location as you. We do have a couple of people in California on the West Coast, like Apoorva on the call, and also Seattle as well. So welcome, everyone. We'll get started in just a minute, but please make sure you're settling in and letting us know where you're tuning in from. Okay, it looks like we have a good amount of people. So I'm going to go ahead and get started. I'm happy to welcome you all to today's webinar, Building RAG Applications Using Multimodal Data. Today we have Apoorva Joshi, Senior AI Developer Advocate at MongoDB, who will be taking you through today's presentation and answering all your questions at the end of today's presentation. But before we jump into the webinar, we're going to go over a couple of quick housekeeping notes. This webinar will be recorded and shared via email, so you'll be receiving this email early next week with the recording and additional resources, so don't worry if you miss anything. All participants will be muted, so if you do have any questions, please use the Q&A box for those questions. That box is located at the bottom of your Zoom panel. It says Q&A with a question mark at the top. The chat is for live comments and general discussion only. And there will also be a short survey at the end, so please make sure you are filling it out because we'd greatly appreciate your feedback. Now I'm going to hand this over to Apoorva to begin today's webinar and presentation for you all. Please make sure to remember if you do have any questions, drop that in the Q&A box for Apoorva to answer in the end. Thank you all for attending today's session.
Thanks, Nia, for the intro, and welcome, everyone. Thanks for tuning in to today's webinar and making the time to be here today. So in today's webinar, we'll quickly talk about what RAG is, but most of our time will be spent on discussing what multimodality is and techniques for multimodal RAG. We'll also have a code walkthrough of actually building a RAG application using one of the techniques that I'll be discussing. And finally, there'll be time for Q&A in the end. It might be hard for me to juggle through all my screens while I'm screen sharing and stuff to monitor questions. So if you have questions, definitely put those in the Q&A box and we'll definitely get to those towards the end of this session. All right, so for those of you who are new to RAG, here's a really, really quick refresher. So RAG, short for Retrieval Augmented Generation, is a technique used to enhance the quality of responses generated by an LLM or large language model using information retrieved from external sources of knowledge. And there's typically two parts in a RAG system. There's retrieval, which deals with processing your data so that you can efficiently retrieve the most relevant information from it. And the retrieval process itself, which is where you hear things like vector search, hybrid search, graph-based retrieval, and stuff like that. And then there's the generation part, which essentially involves passing the retrieved data, the user question, any prompts, and also any conversational history to a large language model for it to generate an informed answer to a given question. So let's focus on the retrieval component of RAG first. So like I said, retrieval in RAG, apart from the retrieval process itself, also involves processing the data for retrieval. And the first step you typically hear about when it comes to processing data for RAG is chunking. So what's chunking? Chunking is the process of breaking down large pieces of text into smaller segments or chunks so that at retrieval time, you only retrieve relevant chunks from the vector database instead of full documents. And as you can imagine, this has several advantages, and a big one being reduction in generation costs. And how does it do this? Most LLM providers charge you for the number of input and output tokens you use. So if you have smaller chunks, this means you're passing lesser input tokens to the LLM, and that means lower costs. It also helps to focus the attention of LLMs on just the relevant information instead of having it sift through a large document to find the most relevant pieces. I see someone raise their hand. I can't see
So
ish.
if you are raising your hand, all participants will remain muted. If you do have any questions, please drop them in the Q&A. Also, please adjust your screen settings. As from our end, we can fully see the screen, and a lot of people that's attending can also see the screen perfectly fine too. So
Okay.
please adjust your screen settings so you can fully see what Apoorva is sharing. Thank you.
Thank you, Nia. All right, moving on. So yeah, we spoke about chunking, and it sounds like a great idea, and it works really well for text. But what does chunking even mean, and what would it work? How would it work if your data contains not just text but images, or tables, or a combination of these with text, such as PowerPoint presentations, or you have financial documents or some analytical documents that have text and some graphs and diagrams. And this is what it means to be multimodal or having multiple modalities. And modality essentially means, in the context of AI these days, means different types of data. And in today's webinar, I'll be focusing on images and text, so two different modalities. But multimodal also includes other types of data, such as audio and video, and I don't know what else. But yeah, at least those are the common ones we hear about. So in working with multimodal data, regular chunking doesn't quite work. Here's an example of a document where you'd struggle with chunking. So you have some text, and then you have this diagram, and you want the LM to extract insights from both of these. So you could chunk the text in this document, but what about the images and tables, right? So we need something more or different here. And there are several ways to tackle this. One way to do this is using specialized machine learning models like vision transformers or object recognition models to first identify and extract the text, image, and table elements from your document. And there's several tools out in the market to do this at this point. Like Llama Index has, I think, a tool called Llama Parse that will do this for you. Or there's a tool called Unstructured that does this. So essentially, yeah, like once you have those elements extracted, then you'd essentially chunk the text elements as usual, but you would instead summarize the images and tables. And then once you've created those summaries, you would create embeddings of the text chunks and the summaries using a text embedding model. So this way, in this technique, you're essentially converting everything to the text domain and using text embedding models to embed all your data. Another technique, kind of similar to the previous one, wherein you still extract the text and non-text elements and you chunk the text, but instead of summarizing the images and tables, you would embed these using a multimodal embedding model and also embed the text chunks using the same model. So what does multimodal embedding model mean, right? So multimodal embedding model essentially maps multiple types of data into the same vector space. So essentially, it could take text, images, audio, video, whatever it's trained on, whatever different modalities it's trained on, and map them to the same vector space, high dimensional vector space. And in today's webinar, we'll look at a multimodal model that can handle both image and text. So the techniques we were just talking about, while they are quite promising for multimodal data, they come with some limitations, right? So first of all, they face the same drawbacks as chunking. So the big problem with chunking that we hear about is context loss at the chunk boundaries, which is why techniques like parent document retrieval or metadata prefiltering are becoming popular, where you add back the context that was lost during chunking, either during retrieval or generation. Also notice how complex the data processing pipeline becomes, right? You need a vision transformer or object recognition model to extract all the elements and another call to create summaries in addition to the chunking and embedding itself. So pretty complex extraction pipelines. And another limitation with a lot of embedding models so far has been the architecture of the models themselves. So until recently, the architecture of most multimodal embedding models for text and images was based on OpenAI's CLIP model. So in this architecture, text and images are routed through separate networks, like you can see here. So based on the input, it'll get routed to a image tower or a text processing tower. So routed through two separate networks to generate embeddings. And this results in something called a modality gap, where irrelevant items from the same modality end up close to each other rather than relevant items of a different modality. So in the CLIP model, for example, since it's dealing with images and text vectors of irrelevant text might appear closer together in vector space rather than text and images corresponding to related objects. So as you can see here, you can see that all the texts are kind of mapped in this region of the vector space and images occur here, although we see that this piece of text is closer to this image. So that's what is the modality gap. But this has changed with the advent of something called vision language models, and then which are new transformer models or generative models that can actually take in images or text and generate images or text. But then there are embedding models that are based on this architecture. So instead of it just has the encoder part of this architecture and not the decoder part. So with these models, both modalities are vectorized using the same encoder, ensuring that both text and visual features are treated as part of a unified representation rather than distinct components. So with these models, all you need is screenshots of documents containing interleaved text and images, and the model will ensure that the contextual relationships between the visual and textual information is preserved. In today's webinar, we'll be using a vision language model-based embedding model from this company called Voyage AI. And the team at Voyage AI has done extensive evaluation and benchmarking on their models, and they found that this architecture significantly outperforms CLIP-based architectures for documents with varying proportions of images in them. But we won't just we like to take benchmarks with a grain of salt, so we'll actually check this out on a data set of our own in today's webinar. So essentially, with this new VLM-based architecture, the data processing pipeline for multimodal RAG, or at least the retrieval component, gets greatly simplified. All you need is, given a set of documents, obtain screenshots of these documents, and let the model do the rest. And finally, the end-to-end pipeline for multimodal RAG then looks something like this. So given a set of documents, you'll first generate screenshots, and then you'll embed these images using a multimodal embedding models and store those embeddings with any additional metadata into a vector database. We'll be using MongoDB. But of course, you don't want to store the raw images themselves in MongoDB because you might run into like the storage constraints of the documents in Mongo. And it's also cheaper to store just raw data into blob storage. So when you generate those screenshots, you do two things. You create embeddings and write those to MongoDB, but you also write those raw raw images themselves to some form of blob storage. This can be S3, Google Cloud Storage, or whatever the Azure equivalent of this is. So then given a user query, you would pass that through the multimodal embedding model as well, perform vector search to get the most relevant neighbors of that query in vector space and get the image IDs for those. Remember, we've embedded screenshots, right? So get those image IDs for those screenshots and make a query to your blob storage to actually get the images. And then you'd pass those images to a multimodal large language model. And this is important. So notice that the LLM that I'm using for generation also is a multimodal LLM. This is because we want the model that's generating the answer to be able to make sense of multiple modalities as well. So yeah, you need a multimodal embedding model at the embedding stage, and you also need a multimodal LLM at the generation stage to finally get back the answer. Now, you might be wondering why Voyage AI. So for those of you who missed this news, we had some really exciting news a few weeks ago where MongoDB joined forces with a company called Voyage AI, which is one of the leading providers of embedding and re-ranking models in the AI space right now. And in the coming months, we'll be integrating all of their embedding and re-ranking models into MongoDB Atlas, including this VLM-based multimodal model. But for today's webinar, let's at least use the model along with MongoDB Atlas vector search to see how well it works with multimodal or mixed modal data. And with that, that's enough talking. I'm going to get into some code. Oops, looks like I got some. Use. I think we should be good. All right, so let's look at some code, right? So we are going to do a few things in this coding session today. First, we are going to look at how to use Voyage AI's multimodal embedding models. Is my screen good? Unable to see your screen.
I'm able to see your screen. From
Okay.
here, please let us know in the chat if you're able to see the screen, but you're good, Apoorva.
Okay, sounds good. All right, so going to do a few things here. We are going to see how to use Voyage AI's VLM-based embedding model. We are going to see what the full pipeline of processing raw documents, getting screenshots, dumping them into blob storage, and also generating the embeddings, putting them in MongoDB, how that whole process works. And we'll also use, for generation, Gemini Flash 2.0 from Google, which is a multimodal large language model. So we'll walk through that whole process of how a multimodal RAG setup might look like. All right, so first things first, I'm going to install libraries that I need. So we have PyMongo, which is MongoDB's Python driver. Actually, let me also paste the link to this notebook for you all to look at later. So this is our GenAI showcase repo, which has a pretty exhaustive list of examples on how to build RAG systems, agents, all that good stuff. And this is the notebook that I'm walking you through right now. I just put that in the Zoom chat. All right, moving on. So yeah, we have PyMongo here, Voyage AI, which is the Python client for Voyage AI, Google GenAI, which is the Python library to use Google's embedding and large language model through GenAI Studio, Google Cloud Storage, because this is the Python client for Google's cloud storage, and that's where I'm going to be writing my raw images to in this tutorial. And then we have sentence transformers. So we are also going to be comparing the Voyage AI VLM-based model with a clip-based model, and that's available on Hugging Face. So I'm using this library to download that model from Hugging Face. Then we have PyMU PDF, which is a library to like analyze and manipulate PDFs. Pillow, which is an image processing Python library. And then these are just Python libraries to like display progress bars and retries. So let's make sure I ran that. That's done. The first thing we want to do is just set a bunch of prerequisites. So I'm setting my MongoDB URI. You need the URI to connect to a MongoDB cluster. And you do that using this connection string, and you obtain that from, this is MongoDB Atlas. I'm looking at my cluster. So not going to go through how to actually create a cluster. We'll link you to resources to do that after the fact. But right now, I have a cluster created. I just want to connect to it. So I'm going to go to my Atlas UI, go to clusters, say connect. I'm going to connect via drivers. So I'm going to go to that. And then this is where I'll find my connection string. So I've copied that and I'm going to put that here. Okay. All right. And another thing I need is a YJI API key. So I'm going to be using YJI embedding models, and the easiest way to use those is through their APIs. So I need an API key to use those embedding models. So let's do that. Yeah, not going to get into the steps to obtain that API key, but it's pretty simple Google to see how to do that. I also need an API key for Gemini because I want to use their multimodal LLM. So let's do that as well. I've just gotten the keys beforehand just to save time right now. Okay, so prerequisites are good to go. First thing we want to do is let's download a PDF document that has images and text. So I'm going to do that using request and PyMu PDF. So the document we are going to be working with today is the DeepSeek paper. So if you look at this paper, it has a bunch of text, it has diagrams, it has kind of a table of contents, and also like multiple tables containing results and whatnot. So yeah, tables. So it has a good mix of text, tables, and images. So it's a good data set to experiment with. So here I'm just getting that PDF, reading the response from that link as an in-memory file object. And then I'm using this library called PyMU PDF to open the object as a PDF document. And if you have a bunch of PDFs locally, then that makes the process just that much easier. But I didn't have one lying around, so I just downloaded it. Okay, so the next thing we want to do is two things. We want to write the raw images itself to Google Cloud Storage, and we want to generate embeddings and write those to MongoDB. So let's do the cloud storage bit first. So for that, you do google.cloud import storage. This is how you interface with Google Cloud Storage using their APIs. And you need to set a Google Cloud Storage project and the bucket where you want to write your data to. Set that. And then I'm going to write a function that's going to do the data upload. So this function is going to take a key, which is what I want the name of the object to be, and then what data to write to that that object. So the way to do that is they have this concept of blob where you first define like a placeholder for the object you want to write to GCS. And then you pass in a byte string that you want to write to that blob and upload that to Google Cloud Storage. So this is what this function is doing. Create an empty list to accumulate some process documents into. And then this is the function where I'm iterating through the pages of the PDF that I created previously. And then the first thing I do is rendering the PDF as an image using, what's this? Yeah, this PyMU PDF has a bunch of functions for analyzing and manipulating PDF. So that's what I'm using to render the PDF as an image. Then I convert the image to in-memory bytes and specify what the format of the image needs to be when I actually write the image to GCS or even like work with the image downstream. And I'm creating a key name of the object in GCS. So it's going to be of the format multimodal RAG. And then this is essentially the page number.png. And then I'm going to use that helper function that I created from before to write each page of the PDF as a separate image to Google Cloud Storage. And this is just like, this is some form of chunking of the document. The document has like 22 pages. So I'm going to write 22 images to GCS. So you still have like enough information in each page, but you don't, so you're still doing some chunking in a sense, but yeah, but you're retaining a good amount of information in each chunk, if you will. Cool. So you're going to upload the raw image to S3 to GCS, but you're also going to extract some metadata from the image itself. So you're extracting the image bytes themselves, at least temporarily. We won't write this to the final documents in MongoDB, but at least temporarily, we are going to keep these here. But this is the metadata that we'll write to MongoDB as well, which is the GCS key or the reference to the image in GCS and the width and height of the image. And I'll show you how this becomes important later on. So let's go ahead and run that. Oh, thought I ran that. Okay. Oh, I missed. Sorry, my bad. Okay, missed this bit here. These are just the names, but I actually need to instantiate. So first we instantiate the GCS client and the bucket itself, which is what I'd forgotten. Okay, so now that upload is happening, so right now it's uploading the images to GCS and it's extracting that metadata and creating that preliminary list of documents that we want to write to MongoDB as well. So that's done. Let's see if I can show you images in GCP as well. The upload's done. We want cloud storage buckets. Okay, so we have that here, multimodal RAG. And you see that these are, we have 22 images sitting here. So these are just the raw images, and each image has one page of the PDF. All right, moving on. So the next thing we want to do is add embeddings to, we also want to write documents to MongoDB with embeddings and some metadata, right? So let's do that. imports. And we are going to want to evaluate two different models. One is the VLM-based model from Voyage AI and also a clip-based model. So we are going to require two embedding models. So the Voyage AI client to generate embeddings using the Voyage AI model. And then I'm going to grab a clip model from Hugging Face using the sentence transformer library. So I'm going to write two helper functions, one to get embeddings using YGI and one to get embeddings using clip. So this is the helper function for YGI. So say the way to do it is client.multimodal embed. That's the method we'll use. And the inputs need to be a list, even if whether you're embedding one string or image or a set of them, they always need to be a list. Then you specify the model you want to use. We are using their latest multimodal model called Voyage Multimodal 3. And then you also need to specify the input type. And this needs to be either query or document. You might think it might be text or image, but you don't need that here because Voyage recognizes whether the input is a text or image automatically. But yeah, the input type here is going to be query or document. So when you're embedding the documents to create your knowledge base, you set the input type to document. And then when you're embedding the user query to perform vector search, you'll set the input type to query. Have that. And here's the other helper function for the clip model. And that's as simple as saying clip.encode. And I think sentence transformer has some code under the hood to distinguish whether the input is a text or image. Okay, so we have that. Create a list to hold those embedded documents. So yeah, we are going to iterate through the documents we had previously. So each document here has the raw image bytes and some metadata. So using those image bytes, we are actually going to open the image and then pass it to each of those embedding helper functions. So we are going to generate two embeddings. One is using the YGI model and another using a clip model. And this is also a good lesson in how to evaluate different embedding models, right? So yeah, pay close attention to this bit as well, because this is a problem that you might run into when you're building like enterprise grade applications where you want to experiment with different embedding models to pick the one that's performing the best. So yeah, you'll add both the embeddings to the same document, and then you'll finally remove the image bytes because we don't need to store the raw image bytes in MongoDB. Okay, so we're going to run that. Few seconds. Okay, so that went through. Let's see what keys we have. So we have the reference to the image in Google Cloud Storage. We have the height and width of the image, and then the two embeddings from two different embedding models. And now we want to ingest these documents into MongoDB. So let's create a MongoDB client and then make sure that we are able to connect to my cluster. Then we set the names of the database collection and vector search index. We're going to need all of these in just a second. So we connect to a database called MongoDB and collection called MongoDB RAG in this step. And we are going to delete any existing documents from this collection. And finally, insert documents, these new documents into that collection. That went through super quick. And then, so we are going to want to search through these image embeddings using vector search, right? And remember, we have two embeddings in our document. So in MongoDB, you can create a single vector search index with two multiple vectors, essentially. So essentially, this is the full vector search index definition, but you can have one definition for multiple definitions for different embedding models. So you give a name to the index, you specify the type, it's a vector search index. And then here you have one object for the voyage embedding model. So you're going to say this field is of type vector, and the path to the vectors is voyage embedding. For this embedding model, the number of dimensions is 1024, and we are going to use the similarity metric, which is cosine. And then for the other one, similar looking object, but we have a different path because we want to point to the path of the clip embeddings. And the number of dimensions is also going to look different because this model produces embeddings of different lengths. We set that, and then we create the vector search index. All right, that's happening. So now we are going to actually define the vector search function itself. But let's think about what we want to do after vector search, right? So using vector search, we want to get what the closest, most relevant documents to the user query are. But in our case, we only have like the references to the raw images. So we need to get those references, and then we need to make an additional call to Google Cloud Storage to actually get the images and pass those on to a multimodal LLM. So we are going to write two helper functions here. The first one is actually getting the image from Google Cloud Storage using the key or pointer to the object. So similar to before, you create that blob and then download the image from GCS as bytes to that blob that you created, and then we'll return those image bytes from this helper function. And the other thing we want to define is a vector search function, and it does a little more than that. So because we are going to want to evaluate two models, we are going to take in the user query as the input, the embedding model that we want to generate embeddings with, and then this function is doing a little extra. So when we are just testing out this function, I want to display the individual screenshots of the pages as well. So I have like some functionality to display images too. So the first thing we want to do is create an embedding for the user query. So we are going to check which model we want to use for embedding and create the user embedding based on that. Then this is the vector search pipeline itself. So the first stage is the $vector search, and this is important. In MongoDB, the first stage always needs to be vector search, and you can follow that with additional aggregation stages. So here I'm going to specify the index name, the query embedding, the path to the embeddings in my documents. And remember, this is dependent on the model. We defined this before. And how many candidates to consider during vector search. And finally, how many documents to return from the vector search. We said, give me the top 5 most relevant documents. And then I'm using the project stage to only project certain fields from the returned document. So I want to definitely project out the Google Cloud Storage key so that I can use that to get the images from GCS. Then the height and width of the image and we'll use this to actually display the images in just a second. And then the vector search score. I just like to see that to see what the score of each of the returned documents is. And then finally, I'm going to execute the aggregation pipeline using this aggregate method. And here I'm essentially aggregating, extracting just the keys from the returned documents. And finally, this function is going to return just the GCS keys. All right, have that. Let's test that real quick. So here, this is my user query. I'm saying I want to use voyage to embed, and I'm saying display images to false. I just don't want to have to scroll through large images, but I just want to make sure that things are working. Cool. So here I got the list of GCS keys. We're going to do the same for clip. So notice that we see slightly different results from the two models. And when we evaluate, we'll see how this actually, which one performed better. But yeah, for now, just note that they're producing slightly different results. Okay, so now we have a way to retrieve results using vector search, and we also have that function to actually retrieve images from our blob storage. So the next step is to actually code up the generation part of our multimodal RAG pipeline. And we are going to use this LLM from Google. It's a multimodal LLM. So to use that, we first instantiate the Gemini client and specify which LLM we want to use. We are using Gemini 2.0 Flash. Then we have a function to actually generate the answer. And this one is going to take the user query as input. And again, the embedding model to use because we've embedded the vector search function here. So first thing that this function does is it gets the GCS keys from the vector search function. So performs vector search to get the most relevant documents to the user query, gets the GCS keys for those PDF pages. Then it actually gets those PDF screenshots from GCS. Then we have a system prompt here, pretty simple, just says answer the question based on provided context. And if context is empty, say, I don't know. And the context here is actually going to be the images extracted from GCS. And then we pass these to the Gemini model. So the way to do this is client.models.generate content. You specify the LLM, and under contents, you have the messages to pass to the LLM, which is, in this case, is the prompt and the images. And then the config specifies any additional parameters. So like temperature, max tokens, things like that. So let's run that. And let's test to make sure that this function is working. Okay, that works. So essentially here we retrieved the images using the voyage embedding model and passed those to the Gemini model. And here we are going to use clips. So let's see if the answer looks any different or if it's the same. Okay, slightly different answers from both the models. So which means like using different embedding models upstream is also going to impact the answers downstream. I'm sure you've seen these if you've built RAG applications so far. And the last thing we want to do before we open the floor for Q&A is I just want to quickly show you how to go about evaluating different embedding models. So I've created this toy evaluation data set. Consists of a few things. It has a set of questions. It has some ground truth answers that I wrote up with the help of another large language model. I think I used DeepSeek. And it has the page numbers, a ranked order of page numbers of which page is the most of the top 5 most relevant pages to this question. And in decreasing order of relevance. So here, the page number 6 is the most relevant to answer this question, and 13 is the least relevant in my top 5 list. And one other thing I've done is, because I want to see how good each of the embedding models are at extracting insights from images and text, I've created a list of questions that can mainly be answered from the images in the paper that we are looking at. And then I have a set of questions that can be answered based on the text. So that way I can add a little more granularity to my evaluation. And actually, I think I'm running out of time. So I'm just going to switch to a notebook that I already have and walk you through that. So continuing from where we were. Oops. All right, so I have my evaluation data set. I'm going to use 3 metrics to evaluate the CLIP and Voyage AI embedding models. So we have reciprocal rank and recall at K, which are retrieval metrics. So reciprocal rank, basically for a given query, it measures 1 over the rank of the first relevant item. And in simpler terms, what this essentially measures is the effectiveness of the retrieval system and measures whether or not relevant items, the most relevant items, are being ranked higher in the retrieve list rather over less relevant items. So that's what this function does. Then we have recall at K, and this essentially measures the proportion of relevant items in the retrieved list and essentially indicates how many of the relevant items you were able to successfully retrieve. So yeah, you pass in the ground truth list, which here in this case is the list of pages. And you also pass in the retrieved list of pages, and you pass in K, which is at what position you want to calculate the recall. And then the recall at K essentially is just going to be the intersection between the ground truth set and the retrieved list of page numbers. And here's a little helper function to actually extract the page numbers from the GCS key, because that's the only place where we have that page number, and it's a simple regular expression matching. And the other metric that we are using, because we saw that even the answers from the LLM were a little different based on the embedding model that we use. So this is a metric to measure the generation itself. So the way we are going to do that is by looking at the alignment of the LLM generated answer with the ground truth answers that we have in our evaluation data set. And if you have the time, then I definitely recommend getting a bunch of human experts to actually measure this alignment, but I've taken the help of an LLM to do that. And this is a pretty common technique for evaluation that we see in the wild these days, which is using a strong LLM as a judge for measuring LLM-generated results. So yeah, here I just have a simple prompt to guide the LLM on how to measure the alignment between the LLM generated answer and the ground truth answers in my evaluation data set. And finally, this is the function where I actually run the evaluation. So I'm going through all the entries in my evaluation data set, and then I'm extracting the question and ground truth answer, and also the ground truth or relevant page numbers. Then I'm retrieving the GCS keys using that vector search function that we defined previously. And I'm going to get the retrieve page numbers from that function. And then I calculate 3 metrics, which is reciprocal rank, recall at K, and alignment. And I do this for every entry in my evaluation data set. And finally, I calculate like the means and averages to get that average over my entire evaluation data set. And I've done a few different evals here. So as I was showing you in my eval data set, I had some questions that could be answered only based on images and some that could be answered only based on text. So my first eval is to see what the performance of each of the embedding models looked on the image-based question. So with Voyage, I was able to achieve a mean reciprocal rank of 1, which means the model was consistently ranking the most relevant results at the top of the retrieved list. And this is important because there's been research to show that at generation time, LLMs focus on information that was given to them earlier than later on. And then the recall is 0.68, which means we were able to extract about 70% of the most relevant pages in that top 5 list. And then we have faithfulness, or this should have been alignment. I don't know why it says faithfulness. But anyway, the alignment is 3.4, which means like it is pretty decently aligned with the ground truth answers. And take this one with a pinch of salt because it is a pretty subjective metric. So I would say focus on the retrieval metrics because they are more deterministic. And we do the same for CLIP. The MRR is slightly lower. And the recall is slightly lower as well, which means the CLIP model is slightly worse than the Voyage AI model at retrieving the most relevant results at the top. And then these are metrics for the text-based questions, slightly lower for both models. Actually, wait. Yeah, Voyage is slightly lower, looks like, for the text-based questions. But I know that in my evaluation data set, the text-based questions are slightly ambiguous. So yeah, like that was just my way of showing you how that would work. But when you are generating evaluation data sets, definitely that's a pretty time-consuming process. You want to get that right. You want to get multiple experts weighing in on that process. Here, it was me and an LLM. So there is some ambiguity in there. Right. So there's that evaluation. And then here's the overall evaluation. So overall, the MRR and recall from the Voyage AI model are better than the CLIP model. I'm not focusing as much on the alignment metric just because, like I said, it's a more subjective metric. So yeah, that's it from me. I know there was a lot to take in, so I want to move on to questions for a little bit. Guessing there are some. There's also the survey that's been already put out.
Yep,
So
we just dropped the survey, so please take a moment to fill that out.
yeah.
While Apoorva goes over the Q&A that you guys have asked. Thank you for sharing so many questions with us. So make sure, and someone asked, can you share the notebook?
Yes, I'm
Please.
putting that here again. That's the notebook. I'm gonna go back
When
to,
Apoorva just shared the notebook basically in the chat, so please make sure you are clicking on that. And we're going to start with the Q&A now. We probably won't
yes.
get to every question as we only have a couple of minutes, but she'll get through as many questions as she can. Thanks, everyone.
Thank you. All right. Getting to straight to the questions. Someone saying, please stop the survey again. So Nia, I'll let you deal with that one. All right. Question 1. How can these be called as multi-AI agents, each for text, element, image, and videos? That's interesting. So you're saying one agent for each modality. Like you can do that, but the whole point of multimodal models is to be able to for a single model to be able to make sense of multiple modalities. So I think if you use multimodal models in your pipelines, that'll just greatly simplify your pipeline itself. How is retrieval quality evaluated? I think we touched on that a little bit. So I used metrics like mean reciprocal rank and recall at K, but you could also add precision at K or NDCG. Yeah, classic retrieval metrics work here as well, as long as you have the ground truth rankings and stuff. Okay, coming back to the final slide on the pipeline, it is still possible to combine it with standard chunk strategy. I mean, using the chunking strategy with a regular LLM. Yeah, it's possible to combine it with a standard chunk strategy. So in my case, I was essentially chunking each page. But if you wanted to do less than that, then yeah, you could have some data processing to actually break down the page even further. But like my results showed that I was able to achieve reasonable performance just embedding full pages. But yeah, uh, if you want to improve performance, then you can try a few different strategies. Is there a way to work with Voyage using Node.js? I'm not completely sure. I would just do a quick Google to see if they have a JavaScript client. If they do, then the answer is yes. How secure is Voyage embedding model using their API key? Do the documents or images get stored on their end? What is the privacy policy? So no, the documents and images, so like we were seeing, right, they don't get stored on Voyage AI's end. Or actually, I don't want to speak to that. Like I would look at their privacy policy and agreements to see what they say about what they do with your data. So definitely check those out to get a better understanding of what they do with your data. Like I don't think it's as much a question about their usage through an API key. The important question is what are they doing with your data, which is a totally valid question. But yeah, read their disclosures and terms and conditions. How large is the recommended MongoDB cluster to be used with Voyage AI as being presented? So I'm using a free cluster, but yeah, it depends on how large your data set is. The nice thing is we aren't storing the actual images in MongoDB, so that's going to significantly cut down costs. So all you're going to really store into MongoDB is the the embeddings and some metadata. So the documents are going to be pretty small. Let's see what my documents look like. Oops, not that. 2, 1. Okay, I can report back on that later. I don't know what's going on here right now. But yeah, the documents are pretty small. When I added the raw image data to my documents, they got pretty big. So I dropped that. We lose some context while chunking the data. How do we overcome this? So yeah, like that's why I was presenting this as an alternative to chunking, right? Like in this case, I'm embedding full screenshots. So I'm keeping the full context of a page in the embedding. Other than that, if you're working with just text, then there's several techniques like parent document retrieval. Then you can actually add some like the full document summaries to each chunk. There's several ways to do that. When you're going through the PDF, you suggested you were converting each page into an image. Why wouldn't we extract all text and then only embed the image in the PDF? Is there a better way to keep everything together? So like the reason I was embedding full pages is to keep everything together. Otherwise, yeah, you would have to like embed the text separately. First, you would have to extract all of them and then embed them separately, which to me is a more complicated pipeline. And like, yeah, screenshotting everything is a way to keep it together. Is there any cleaning of data happening behind the scenes of the PDF provided? Nope. Which is why like I was amazed when I stumbled upon this technique, because it's like literally take a PDF and screenshot it. Are there links present in the document? Can the chatbot retrieve them if the data is chunked at the start? I'm not doing that, but that's an interesting call out. You might just need to add some custom code to make that happen. To mark some of these questions as answered. Okay, links, we covered that. Is Voyage LLM available in AWS Bedrock? I'm not sure, but let's look. In the marketplace, I'll need to look a little more closely to see if it's available through Bedrock itself. Do we need to ensure that the same dimension is used for both storing and querying? Yes, very much so. Same dimension, same embedding models. Otherwise, you might end up with information, your query and the rest of your data ending up in different vector spaces. So same embedding model, same dimensions have to be used.
I think we only have time for one more question.
Okay, let's
I'm gonna
see.
go back to the slide as well.
Yeah. How will the flow change once Voyage AI is integrated with Atlas? Will Atlas offer an integrated service for embedding? Yes, that's right. That's the idea. I think where we are going towards is you point Atlas to your data, and then we'll do the embedding and re-ranking, like will happen automatically as part of our aggregation framework or something. All right, so I think, unfortunately, that's all the questions I have time for. We'll figure out a way to get back to the questions that we didn't get to, but thank you so much for tuning in today. Going back to the slides.
Thank you everyone so much for tuning into today's webinar. Please make sure you are filling out the poll questions. We're about to close them down, but just a reminder that you will receive the recording and additional resources early next week. And if you missed any part of the webinar, you'll be able to watch it at your convenience. Please continue engagement with us in our MongoDB community forums. Let me actually drop that link for you now. Give me just a second. I just dropped the link in the chat, so if for any other MongoDB questions, please use that community forum along with topic-specific questions for this webinar to continue engagement with us. And also, please make sure you're registering for more of our webinars, and I'll drop that link as well. Thank you all for tuning in today, and please continue to reach out with any questions and keep a lookout for the email with the recording and additional resources. Thank you all and have a great rest of your day. And thank you so much to Apoorva for this amazing presentation.
Thank you. Bye.